Well, good afternoon. This is the second in this June Bite-Sized Corrosion series, where we're talking about all things maritime. For those who don't know me, my name is Vanessa Seeley-Fisher, and it's my great pleasure to host today's session. Our Bite-Sized Corrosion webinars are really geared at trying to make corrosion-related information interesting, informative, and hopefully palatable. Let's say digestible. And we hope that you learn something that's new and interesting and makes you eager to continue your journey in understanding corrosion just a little more. I indicated that we started our maritime corrosion series yesterday with such an interesting discussion about some of the corrosion experienced on naval vessels when John Lusty shared his experiences with us. One of the big challenges with marine corrosion is that it takes place in the ocean. And obviously not all structures in the ocean can be as easily removed as a ship, like we spoke about yesterday. And today I'm thrilled to welcome Grant Wallis to the microphone. Grant has more than 30 years of experience as a commercial diver, and he spent some of his time diving for diamonds along the west coast of South Africa, but has devoted much of his career to corrosion-related diving, which we'll be exploring. So a very warm welcome to you, Grant.
Thank you.
Now, Grant, yesterday we chatted, as I said, with John Lusty about the cathodic protection of vessels. And whilst you and I were off air earlier, you mentioned that you've also undertaken inspection of vessels. Now, where would these inspections have value compared with taking the ship out of the ocean?
So the inspections in the water are UWALs, underwater inspections in lieu of dry docking. So generally a vessel will need to be inspected every approximately 2 years. Obviously, dry docking is incredibly expensive, and it also takes the vessel out of service, so there's loss of income. And the inspections that we would do underwater would include hull inspection, paint adhesion inspections, standard of the welds, condition of the welds, condition of the anodes. Is the ICCP working? Is there sacrificial anodes in place? Are they being effective? We would, in certain instances, do potential measurements as well. UWALs are a big part of our work and quite a big thing in the industry.
And I can definitely see the merit of keeping your ship in the ocean where it can do its job rather than taking it out and exposing it to sunshine, which the bottom part of a ship should never be exposed to. I mean, I suppose swimming around these vessels must be very interesting. Just thinking about the size of some of those huge tankers, dry docking would seem almost an impossible task. But talk about some of the challenges there are associated with what you do find underwater and what you're looking for on these vessels.
Sure. So a simple thing like welding underwater, it's very, very difficult. The work underwater is incredibly difficult compared to the work on surface. If there's a current, it's really, really difficult to work. If there's wind swell, if there's waves, generally we would be doing the UWALs in harbour. If the vessel comes in to offload, we would do the work then. It does sometimes happen out at sea at an anchorage, but then obviously it's very much more exposed to the elements.
Yes, I can imagine.
And becomes a little bit more difficult. If we're welding underwater, it can be done. Obviously, we have to use specialized equipment for it. We only use DC welding equipment, no AC. It tends to be a little bit shocking. Welding underwater is complicated. If there's currents, if there's wind swell, as I mentioned, it becomes very, very difficult. We generally tend to weld at deeper depths so that we don't have any interference from surface conditions. You can imagine if you're trying to weld, if you're welding topside, you're nice and stable, you can actually lay down a decent weld if you're nice and still. If you're in the water and you're moving around, there's no way you're going to be able to weld and have it pass any kind of inspection, or you can't even guarantee the continuity of the weld, and you could lose the anode. So it does become quite complicated and difficult.
I can imagine, Grant, and I don't have much experience even with welding in the air, but I can imagine that if the plate that's specified is too thin, you might have some challenges where that's less of a constraint. I think you described it as topside. Is that a valid statement, that you need to be careful what you're using?
Absolutely. Welding underwater, we have to weld with a much higher current. So if the plate is too thin, we actually end up burning the plate away. Similarly, sometimes people will specify a galvanized plate. Obviously, it's in water. You want it to be galvanized for protection. But galvanized plates, you can't weld a galvanized plate at the best of times, certainly not underwater.
Of course, yes.
Galvanized plate just rejects the welding completely underwater.
Now, if welding is so challenging, what about using nuts and bolts? Now, obviously, I'm concerned about those losing electrical connectivity by forming a dry joint, which seems bizarre when we're talking about something underwater. But would nuts and bolts be a suitable solution, or do you have challenges with those that we haven't thought of either?
Generally, welding is specified because, again, underwater, you would want to use stainless steel nuts and bolts. The problem with stainless steel nuts and bolts is that over time, when you try and undo the nut from the bolt, it actually binds and you end up shearing the nut off. And then you have a stud that doesn't have any thread on it, and then you basically you end up welding in any case. You have to weld a nut on. So if you're going to be welding a nut on in 90% of the cases, you might as well just weld the anode on and be done with it, and then you don't have to deal with dry joints.
Okay, so clearly nuts and bolts are a bad idea underwater as much as above water. And I guess our recommendation then to engineers is to avoid nuts and bolts, especially for objects that are going to be replaced or repaired underwater, and look at welding, but looking within the constraints of welding underwater as well. And yeah, the complexities of that seem to be quite challenging. Now, those aren't the only constraints, I'm sure, with installing anodes. Practically, I mean, we think of small anodes used in the water industry, which are reasonably, if I can say, manhandleable, quite easy to maneuver. Do you have any constraints with using anodes offshore as a diver?
The biggest issue we have with it is the size of the anodes. Diving interventions are massively expensive. You can imagine it's the vessel, it's a full dive team, it's the support crew. It ends up being very, very costly. So generally, the maximum amount of sacrificial material needs to be put down as possible. So we will end up installing anodes, either zinc or magnesium generally, anywhere up to 250 kilos per anode, which is, it's a monster. So moving them around underwater it becomes difficult. We have to use lever hoists and come-alongs and all that sort of thing to move it around. Obviously, they're also quite big, so if there is a current, they do tend to move around in the current as well. So there's that consideration that needs to be considered.
Taken into account, yes.
Yeah, that's the word I was looking for.
That's quite interesting that we don't think of the practical constraints of the diver installation. We have these grand ideas of, well, let's use this anode. And would you only be installing these anodes on ships, or do you install them on other structures, sort of offshore rigs and so on? Would that be something that divers would be doing, or is that done from some sort of underwater vessel?
Divers would be doing that. We install anodes on steel structures, whatever they are. If there's a caisson, a steel caisson that is not protected with a impressed current, we would install sacrificial anodes on semi-sub drilling rigs. Definitely a lot of anodes there. Jack-up barges, a lot of anodes, sacrificial anodes that need to be welded in place. So yeah, there are a lot of instances pretty much anywhere that we would be installing. Even deeper water, where divers can't get to, ROVs will actually get involved in that, although that's not really so much sacrificial anodes. That would be more the ICCP side of things. It wouldn't be a direct mount onto the pipeline or the structure. It would be a skid that's got anodes on it, with a cable going to the structure, and then that would be attached generally via a bolt, because that would generally be the pipelines. So obviously welding on a pipeline, especially if it's a explosive pipeline or a flammable pipeline, would not be a good idea, and definitely not allowed.
It could be a little bit of an explosive situation.
Definitely, yeah.
Corrosion protection obviously isn't only achieved by anodes and the use of anodes, either sacrificial or impressed current, but we always say that the primary form of corrosion protection is from coatings. And I've got a couple of coatings related questions. The first one is, how do we apply them underwater? Can they be applied underwater, or are there constraints to that?
They can be applied underwater. Generally, try to avoid it if you can, but that can be applied. Small areas, and then it's generally, we would use a 2-part epoxy.
Mm-hmm.
Those are the most commonly used, and they can be applied by brush, or we usually use a thicker epoxy that can be almost rolled into a ball, and then that's actually applied, and then that gets smeared out and covered.
Okay.
Obviously, no spray paint. That's not going to work. Conventional or airless is not going to work. But that leads to its own problems as well, obviously.
Well, I was just going to ask, I mean, we always talk above ground when we talk about coatings. You want surface preparation to be pristine. And the big thing, you never want salts. And in the ocean, asking for no salts is the impossible.
It is.
So I guess that can be very challenging.
It is. Coating underwater is your last option. You would prefer not to coat underwater, preferably have everything prepped topside and then placed into the water. But in certain instances, that's unavoidable. If you're welding things in place, obviously you need to remove the paint, weld it in place, and then cover that with epoxy.
Mm-hmm.
Then we would cover that with an epoxy, but you don't get rid of all the salt. Mm-hmm. Or chlorides that are on the metal. So you'd apply it, and you'd seal it effectively, but you can't guarantee that you don't have any holidays.
Right.
And there isn't a way to test for holidays underwater. Again, a high voltage AC holiday detector, no.
When we started our conversation, you indicated that you do some coating adhesion tests underwater, and that's quite an interesting concept to me. How do you test for coating adhesion on buried structures?
Generally, it would be visual. If you notice that if there are areas where it is flaking, you would then actually use a dull patty knife and actually see if you can actually pull it away. Also,
and if you can, then you need to get your repair material out and cover it up.
If we notice any kind of delamination, we're not going to get into repairing it straight away. Then that has to be investigated more thoroughly. Chances are we wouldn't actually end up doing the investigation because the vessel is in port for a very small period of time. So at the next port of call, they would then have another team set up to actually go in and do a more thorough investigation. And then, depending on how bad it is, repair it there and then, or wait for the next port of call. And while it's in transit, actually come up with a plan to actually fix it.
Yes, I imagine that the coming up with a plan bit is going to be quite the challenge. Yeah. And we've spoken briefly about adhesion testing of coating, presumably that was applied topside and now has deteriorated in the ocean when you talk about doing adhesion testing. But just your talk about applying the coating underwater makes me be very concerned about its adhesion, because yeah, we've got water under there, we've got salts under there, we've got probably a compromised surface. And I remember many years ago now, a brief excursion into endeavoring to do some coating repairs underwater. And we did not have a very happy solution to the problem. And in fact, yeah, we never resolved it. So I can imagine that paint sticking being applied underwater is a very specific formulation that would be required. And I'm sure
it is
highly costly.
It's highly costly. It's very specialized. You can never obviously guarantee the work because of all those factors that you mentioned previously. Rust that can't be removed properly, salts that are not removed. So generally, the painting repair won't happen in water. That will have to wait until it gets into dry dock. But if it is severe, then you could possibly like a on the fly remedy would be to actually weld in a sacrificial anode in the area that's actually rusting quite badly. If it is, try and mitigate it and make sure you can get through to your next dry dock.
You haven't only been diving around ships, and we've mentioned some brief discussion about where you've applied anodes and so on to offshore structures. But tell me a little bit more about diving associated with offshore structures and what kinds of structures that could include.
So the offshore structures, I haven't worked on them, but the wind farms in the North Sea, wind farms are a massive thing. I've never worked on them, but certainly there would be a lot of work. Offshore structures would be your calm buoys, which is it's basically a discharge point. So there will be a pipeline coming up to the calm buoy. A tanker will come will tie up onto the calm buoy, and they will discharge or receive product, and then head offshore or whatever. So calm buoys, flames, pipeline in manifolds, pipelines themselves. Yeah, there's a huge amount of different offshore structures that we would actually be diving on. My brother's a inspection diver, and he actually does cathodic protection inspections on pipelines, all sorts of things. Yeah, the advancements in materials, but also the advancements in the inspection techniques and technologies has improved vastly in the last few years. It's pretty much anything you can do topside, you can do in water, except for holiday detecting.
Now, I'm sure you've seen a lot of corrosion of structures that are offshore, and I wonder if you've got some that stand out for you that you'd like to share with us.
I have. The last project I was on, it was for the US Navy on Diego Garcia. We were replacing some structures on the quayside that they come alongside, or the big vessels come alongside on. We were removing and then replacing the piles, concrete filled steel piles, and putting in new H piles, steel H piles. The piles were being removed because the structures on the surface had been condemned. The piles themselves were in excellent condition. I would say probably less than 5% diminution of the steel, and the coating, I think it was a coal tar epoxy, was in excellent condition. Under the water, everything was in excellent condition, but it was it was really amazing to see the ICCP had been working. Some of the connecting rods from the ICCP had actually disintegrated, but saltwater is such a good conductor that the structures that had the ICCP on them were actually still protecting the piles themselves. So, and those were installed in the 1970s, and I would say they were still in excellent condition.
Yeah, it's very encouraging to hear that, because I think we think of offshore structures and sometimes they are not designed with cathodic protection, and this really is an encouragement that you can maintain an excellent condition of something for 50 years with cathodic protection and keep it in pristine condition. And it does make you wonder if they'd applied cathodic protection on the superstructure, whether that would have been saved from being condemned as well. But I'm sure that one of the problems that you've seen quite a lot of, maybe structures that haven't been so well monitored and maintained, has been rebar causing spalling and that resulting in corrosion.
Absolutely. In my opinion, in marine civils, it's probably the leading cause of failure is concrete spalling. That rebar, once it's got salt in it and it's in seawater, it's got salt on it, it's going to corrode, and corroding rebar is just going to cause spalling, and it's just a cascading effect. But yeah, once it's started, it's not easy to stop.
Yes, and I think we don't necessarily give concrete and concrete corrosion its due attention. We did do a series a year or two ago on concrete and concrete corrosion, and it's probably something we could discuss in greater depth. There are some solutions that could be considered, and I wonder if you've encountered any interventions that have been applied with the reinforcing in concrete to kind of stop the corrosion.
So using galvanized rebar is definitely going to help. Also installing anodes, sacrificial anodes connected to the rebar does help, although I've only really seen the anodes used on repairs. I haven't ever seen anodes actually installed in the initial build, which is, I think, something that could definitely be taken into consideration at the design stage. Install the anodes at the beginning. It's going to give you, it's not going to solve the problem, but it's certainly going to give you a longer life before you have to do any reparations.
Well, cathodic protection in concrete is not unknown by any stretch of the imagination. Just not very common here in Southern Africa, but certainly it is used, particularly in bridges in the US. The majority of their concrete bridges have cathodic protection. So it's definitely technology that exists. And maybe it's technology that we should encourage the use of in a little more frequently in structures with which we have.
Yeah, in South Africa, I haven't seen it much, to be honest. Especially concrete that's been installed in formwork that is submerged. There's obviously bigger issues there. And then also in the splash zone. We know the splash zone is subject to its own extreme environment. In those two areas, it definitely would warrant some more thought at the design stage.
When I think about diving, and that's really where we've tried to take this conversation around, is the corrosion that you've experienced during your diving career. Obviously, there are safety challenges with diving that I think maybe we don't take into account, other than the fact that you're choosing to do something where you don't have oxygen directly available to you, which is something I don't understand at all. But your job as a diver tends to take quite a long time. And is that just because, dare I say, you're not very competent, or are there real reasons for your delays?
So if you speak to the client, it's because we're incompetent, and we are generally, diving is a day rate. So it always gets thrown out there, sometimes directly, sometimes a little bit from the side, that we are just pulling the job out to make more money. But it's not true. We want to get home. We spend enough time away from our families. We want to get home and actually enjoy the money that we're earning. So no, there's so many things that impact us. Zero visibility, no stable platform to work on. We floating in the water. You're trying to turn a spanner. You have to brace yourself to just tweak a spanner. Currents moving our tools around. You'll put a tool down, and especially if you're working in the surf zone, you put your spanner down, you turn around, you come back, and you're feeling for your spanner, and it's gone. So then you have to put lanyards onto everything to keep them in the same place. But if you've got 5 tools down there, your lanyards are going to make cook sisters, and you have to deal with that. Hydraulic hoses getting tangled, restricted vision and maneuverability in your hard hat. You've got, I'd say, maybe 30 to 40% of your general field of vision that you would have on the surface. You've got a wetsuit on, you've got a heavy harness on, you've got a weight belt. Even breathing is more difficult underwater. If you're working at 30 meters, you're working at 4 bar pressure, 4 atmospheres. So the air is thick. So when you're working hard, 50% of your energy is going into just expanding your chest so that you can actually get air to do the job. So I promise you, we are not just trying to make the job longer to earn more money. That's not the case.
Grant, this has been absolutely fascinating. Thank you. And definitely has given, I think, some engineers a little bit of food for thought about the expectations that we put on the diving community when we're asking them to do our work for us, because obviously we're not qualified or certified to do it ourselves. Thank you. It's been wonderful. And I've also learned so much about the practical implications about the corrosion measures that we design. So thank you. And I do hope our audience has also found this interesting and useful. Just as we close off today, I just want to invite you that if you've found these discussions on corrosion interesting, I encourage you to take some time to look at some fundamentals about corrosion through our online course, Conquering Corrosion. Thank you, everyone. Goodbye.